So everybody is familiar with awesome learning, and progress in artificial intelligence has been really astonishing in the past decade. So cars self-driving on highways, machines beating Go masters, and cameras categorizing images in a pixel-precise fashion are now sort of commonplace. And this is all thanks to data and label supervised deep learning. And here you see some covers from Nature and Science, highlighting great achievements, finding melanoma in the skin better than radiologists, designing floor plans for chip designs, folding molecules, what have we. Everything is feasible as long as there is data and labels. So the state of affairs is essentially that if you have sort of like a closed world problem and you have a huge amount of data and labels, you can do pretty cool things with deep representation learning. Nonetheless, despite these impressive advances, it is becoming increasingly clear that deep learning networks are biased towards their training conditions, and they do become brittle when deployed under real-world situations that differ from those perceived during learning in terms of data, labels, and objectives. So while we can move in this direction, the bias in representation learning is starting to become problematic. And to attack these issues with these dependence on data, labels, objectives, and fairness, one direction is to go this way. So we move into more real-world settings, but we keep on continuing with the data and label metaphor, so to say. It is becoming increasingly clear that simply scaling up along all these dimensions at training time is a dead end. And this is not only because of compute, storage, and ethical expenses, but especially this is a weird way of doing things, as humans are so good at generalizing robustly in a very data efficient fashion. So there is a need for something new and for something different. Now, many have considered many existing learning paradigms have been proposed already in the literature to account for the limitations of deep learning with the AIDA assumption. So, for example, the distribution gap is being attacked by domain adaptation and domain generalization works, where folks have been learning domain invariance or domain normalization techniques, or augmenting domains in such a way to be generalizable to unseen conditions seen at test time. We also have a label gap, and here that the problem is that label vocabularies change. They are the topic of interest in self-supervised methods, zero-shot, open set, and open world learning. So here you see a teaser image from recent ICSV work from my team, where we relied on clustering video based on flow and then predicting pseudo labels of those clusters using RGB information. So as to embed motion into the representation learning without the need to compute during inference, and in a very data and label efficient way. Another type of problems is the objectives gap, and varying objectives can be covered in meta-learning scheme, and multitask learning, and also in continual learning. And here the challenge becomes to prevent catastrophic forgetting. And then last but certainly not least is the fairness gap. And it's increasingly clear that data contains biases. For example, adverse decisions from image classifiers can create discrimination against members of certain classes of protected attributes, such as age, gender, or skin tone. And of course, we can blame the data set, but it is becoming also increasingly clear that the representation learning can also enhance biases. So in the same way, it can also reduce biases. So here's an example of recent work from William Thong that is to appear at BMVC this week. As of yet, there is no learning methodology in the world, as far as I'm aware of, that can dynamically learn to generalize and adapt across domains, labels, tasks, and fairness considerations simultaneously, and do so in a data efficient fashion. Now, I consider this the ambitious long-term goal of real-world learning. And today I'm going to talk about some recent work from the team that tries to get to real-world learning, and we do so by questioning common representation learning assumptions. So I'm going to talk about today about three of those assumptions. So the first one is to learn. Can we learn without having a label assumption? The second one is about learning without task assumption. And the third one considers learning without a domain assumption. And I will go over these three one by one. So the first is learning without label assumption, and this is joint work with Peng-Wan Yang and Pascal Mettes from the University of Amsterdam, and this appeared at CFPR past summer. And here we consider few-shot learning, but without having any labels. Now, the canonical paradigm is as follows. So here you have five images, 4 support images, including a label, and then the task is to predict what is the type of breed of dog for the query image. And one can train a network that does so in a very effective manner. Now, this can easily be extended to also cover detection. And then simply what one does is, in addition to providing the label to the support images, one also provides a bounding box as additional annotation. And work exists that can do so quite well. Now, in 2019 at ICV, we introduced an algorithm we called Suco, and this stands for Few-Shot Common Object Localization. And here the goal is to localize an object in a query image based on some support images that don't have a label and also no box annotation. And then essentially what the network does is find the commonality between all these images to localize the common object. Now, how do we go about? Well, this was essentially formalized as a network with two modules, one to learn spatial similarity between query and support images, and one for feature reweighting. And the idea here was that some support images are more important, more characteristic, more prototype than others, and you can include this into your few-shot localization problem. Now, this was all inspiration for our work on few-shot common action localization in video. And here the idea is the following. So given a few trimmed support videos, so trimmed means that the action is nicely confined within the boundaries of the video. And we have 5 of those or a few of those support videos. And we don't know what is the activity label. All we know is that they share the same activity. Then what we propose is a few-shot transformer that finds, based on these support videos and a long untrimmed query video. So this is a long video, and we know that somewhere in the video is the action of interest. We don't know the name of the action. We're also not interested in the name of the action or the label. All we know is that the action is shared among the support videos as well. So, and what we're then going to do is find the enclosing spatiotemporal tuplet around the action of interest. So the nice thing of this approach is that it does not need any action class label, nor any temporal or spatial annotations. So here you see the algorithm at work for 1 and 5 examples. So blue is the prediction based on 1 shot, and red based on 5 shots, and both are actually quite good in this example. So on top, you see the 5 trimmed support videos that serve as the example, and the algorithm automatically finds then the spatiotemporal volume around the action of interest. Now, how do we go about? We are inspired by the Detter transformer. So transformers are great. It avoids needle in haystack problems with proposals and anchors and what have we, other kinds of hand-engineered optimizations. And best of all, it provides very powerful relation modeling capability because it's sequence to sequence nature. So we got inspired by this transformer for object detection. I think one of the first successful manifestations of transformers in vision. and we adapted it to the video case, and especially for the spatial temporal similarity, without using any annotations. So I won't go over all the blocks in details, but I just want to highlight one common block. So the common attention block that we define over here, that sort of serves as the workhorse in this approach. It tries to find what is common among source and between query and support videos. It is built on the self-attention mechanism and the non-local structure, and it is extended to self and cross attention. So what we do here, we feed both the query and the support videos and the features thereof into a separate encoder. And because the encoder is permutation invariant, we need to supplement it with fixed spatial temporal positional encodings that are added to both the support and query clip features. And then we let the support videos go through the encoder one by one and concatenate the output. In the decoder, there is a standard transformer decoder. There are 2 inputs, but in our case, there are 3, because we have the support branch, the query branch, and the input embeddings, which are learned from the positional encodings. Now, after this decoding, we have our final prediction, just 3-layer perceptron that's performed on the output with some RealU activations, followed by a set-based projection layer. And this predicts the normalized center coordinates, the height and the width of the boxes with respect to the keyframe of the individual query clips, along with the foreground and background binary labels. And these are then linked over time to get sort of the triplet volume in the video. Now, this is all great. Here you see another example. So here on top, 5 support videos. So we don't know what is in there. We only know that they have some commonality. And in the support or in the query video of interest, we can then find the activity that is common. Now, when we did an ablation for this work, we found some interesting observations. So let's have a look at this plot, which shows on this axis the length of the support video, so in number of frames. Essentially, the conclusion is not so surprising, because it essentially shows that the longer the support video, so the more content you feed to the algorithm, the better the results become. And here we have on this axis the shot numbers. Also, again, not so surprising. The more examples we provide in the support set, the higher the accuracy becomes. So here measured in frame MAP. So more is better, but even if you have only a few frames or a few shots, the results are actually pretty decent. And it became more interesting when we started to inject noise in the support sets. So when we have no noise, we reach a frame MAP of 28.1. So there's a decent results corresponding with this bar over here. And now we start to inject noise in the support videos. So rather than having 5 videos with a common class, we assume that one of them has a video with another class in it, and then performance starts to drop, but not so much actually. And if we add in a noisy support video without any action, it's approximately the same result. When we increase the noisy support videos further, results start to become worse. But again, it's still doing a decent job. And the same holds for injecting noisy frame level videos. So based on this observation, we have been doing some new experiments lately. And this is what we call self-support video instance segmentation. So here the observation is that we can find the support videos also from a large pool of unlabeled video in a self-supervised fashion. So given a query video, like the one on top over here, we find support videos, which we call self-support videos, from a large pool of unlabeled web videos. And these then form the input for a new common transformer that can do video instance segmentation. So this is completely data-driven without the need for any labels or any mask, and you will get pixel segmentations out. Here are some results. So this is the query video. We want to segment the common object, so to say. And these are the self-support examples that were found by querying a large pool of videos. And while only few of them actually contain cows in the meadow, they all contain animals in the meadow. And apparently this is sufficient support, sufficient information to do a reasonable segmentation of the query video. So that is actually quite surprising. Here's another example for bicycles. And although not all of them are human cycling on the road, sometimes it's a skateboarder on the road or another type of vehicle or no vehicle at all, it still can do a reasonable segmentation. So that's quite interesting. And we did an experiment where we looked at what is the influence of the pool of unlabeled video, and we scaled that up. And what we find is that with a pool of 75,000 videos, we could, and 5 self-support videos, we can beat one Oracle support alternative. So this suggests that by scaling the data set size further, we may get into scalable video instance segmentation. So that gives a surprising outcome, because essentially we can do learning without having this label assumption. Okay, so that is the first paper I would like to discuss. This is the second one, where we relax the task assumption. And this is work together with Yingyun, Shantong, and Ling, mostly from University of Amsterdam. And it was presented at iClear last year. And here we look at Metalearning. So Metalearning is a very powerful learning paradigm that can support multiple tasks in its formalism. And essentially it splits the learning problem at 2 levels. So the first one is quick acquisition of knowledge within each task separately. For example, here shown as few shot tasks. And the process, so every task here becomes essentially a data point. So every task is optimized separately. That is the first level, but then there's also a second level, which involved essentially slower extraction of information, where it tries to learn what is the commonality among all these tasks. So the meta learner, so to say. Now here it is shown for few shot learning, but it has also been very effective in reinforcement learning and domain generalization. Now all these meta learning approaches tend to be based on deep networks. The deeper, the better. And in these deep learning networks, the workhorse is batch normalization. Batch normalization helps stabilize the distribution of internal activations when a model is being trained. So given a mini batch B, the normalization is conducted along each individual feature channel for 2D convolutional neural networks. And in a batch, it's easy to compute the first order moments, the mean and the variance. And the gamma and the beta parameters are learned during training. So this performs the normalization. This is great, works fantastically in many shot approaches, but there is an implicit assumption in batch normalization, and that is that it assumes that samples in the dataset are independent and identically distributed. So this means that if you have very small, this assumption is valid for large datasets and large batches, but when the batch statistics do come unstable when your batch sizes is very small, for example, in few shot learning problems. And challenge 2 is the distribution shift between source and target domain, which batch normalization cannot handle very well. Now, one way to avoid this problem is to rely on transductive batch normalization. And here we again, consider the few-shot classification problem. So you can compute best statistics by simply using all available query data that you have in hand. And the more data you use, of course, the best normalization can profit, and your normalization estimates will be better. But the requirement to have all your test samples available for each individual query will limit real-world use. So this transductive setting is not always feasible. This problem was posed and identified by John Broskill et al. When they introduced task norm at ICML 2020. And they identified this limiting assumption of the transductive setting. And they proposed a meta-learning alternative where they leverage the statistics from both layer and instance normalization. And the key intuition behind their task is to essentially have to normalize the task with these context set moments in combination with a set of non-transductive secondary moments that are computed from the input being normalized. And then they have a blending factor between those two sets of moments, which is optimized during meta-learning. And in the paper, they show that this is always better than batch norm, and even sometimes better than the transductive setting. Now, we notice that there is room for some improvement here, and our proposal is Metanorm. And we also leverage the meta-learning setting, similar to task norm paper. And what we do is we infer the statistics from the support set that better match the query set. So that is what we try to learn. So essentially, our Metanorm learns to learn the adaptive statistics that are specific to tasks or domains, for that matter. And by doing so, it is generic, model agnostic, and it can be used with various meta-learning algorithms for different applications and tasks. So during meta training, we minimize the Kullback-Leibler divergence between the distributions inferred from the support set and the distribution inferred from the query set. So by trying to minimize those, we can predict at test time, when we only have the support set, we can predict the appropriate normalization statistics for unseen queries as well. I was talking about Metanorm and how it infers statistics from the support set to match those of a query set that is unseen at test time. So basically how it works is that we try to minimize the distributions of parameters that are estimated for both the support and the query set during meta training. And then we introduce hypernetworks that try to predict those normalization statistics. And we optimize those during meta training optimizations. And hypernetworks are just networks that generate weights for another network. And here we use amortization techniques. So how does it work at meta testing then? Given a test task, the learned hypernetworks take the support set as input, and from this they generate normalization statistics that are directly applied to the query set. And this results, hopefully, in a better normalization. So the key is this Kullback-Leibler term that tries to make the distribution between support and query set similar during optimization. And we measured the effect of this term in an ablation for both few-shot classification task and domain generalization task. And the effect is considerable. So by enforcing this minimization during the meta learning, we can do a very good prediction of normalization statistics. Now, we also compare this with other batch norm approaches. So TBN is transductive batch normalization, CBN is conventional batch normalization, and task norm is the work by others I've mentioned. And we do well on all accounts. And no matter what the underlying meta-learning framework is, so whether it's ProtoNets or MAML, and we also report Versa in the paper, it works for all equally well. because we considered few-shot learning and domain generalization, we also introduced a new real-world learning problem, and that is few-shot domain generalization. So during training, you're only seeing some domains, and the goal is to generalize to those domains that are unseen at test time. And to make it hard, we also do this in a few-shot setting. So we created the problem task definition for this variation of few-shot learning and domain generalization. And we compared also our Metanorm normalization technique. And also here it proved very effective in comparison to existing normalization techniques. So Metanorm allows for batch normalization of small batches across domains, and is therefore a better alternative than regular batch normalization. So that covers the second part of the talk, and now let's end with the third chapter, and this is learning without domain assumption. And this is work with Zehao Xiao, Shantong Zhen again, and Ling Xiao from the Inception Institute of AI. And this work is currently under submission. And here we consider distribution gaps, which are a fact of life. I mean, images come with different styles. Cars can be trained during the day, but have to operate also during the night or in snow conditions or fog or what have we. And medical images from different devices can have their own biases and may appear very different when deployed in the real world. There's lots of work on domain generalization and domain adaptation. Here we got inspired from people doing things slightly different. And the first work is test time training by folks at UC Berkeley. What they do is that at training time, they jointly optimize a self-supervised loss. So here, depicted as a rotation prediction problem, and the main task loss that tries to predict the label that corresponds to the image. Now, at test time, they cannot see the main task label, that is the one they need to predict, obviously, but they can still optimize the self-supervised loss over this single test input. And this produces a new version of the test input, which they then use to make the final label prediction. So this is a nice way of getting rid of the train and test division that is so classical in machine learning, and instead use the test set in a clever way without using its label or whatsoever. So a downside of their approach is that it needs an additional self-supervised model, and it needs some fine-tuning at test time. So some backpropagation is required. Now, another paper that appeared afterwards at iClear last year, also from Berkeley, they had the observations that predictions that are made by a model with lower entropy have lower error rates. And so the certainty of the class predictions can serve as a supervision signal during testing. And that is why they proposed this entropy minimization tactic. So what they do is, given an input, they normalize with mean and variance statistics that can be simply computed per batch. And then they estimate normalization statistics and optimize also channel-wise affine transformations to update online on each batch. And they show that this outperforms the test time training, the previous paper I mentioned. It still has a downside. It needs an entire batch of target samples from the target domain, and it still needs backpropagation. Now we want to get rid of this batch assumption, and instead our key idea is the following. So we want to adapt source domain classifiers based on each individual target sample that we have to classify. So essentially what we do here is that we treat every unseen target sample as a domain by itself. And we propose an algorithm that allows to change our classifiers that we see on source domains to adapt those to the characteristics of the target sample so as to better classify it in the appropriate class. Here we again rely on the meta-learning framework. So in meta-learning, we try to mimic the shift between source and target by using the shift among source domains. That is the main idea. So normally you have the set of source domains and you have the target domain on which you want to do inference. You cannot use the target domain, but if you have many source domains, in our case you need at least 2, you can sort of like during meta training, you can separate your source domains in a meta source domain and the meta target domain so as to mimic the domain shift during training. And by doing so, you can endow your model with the capability of learning to adapt to a given sample also from unseen target domains. Now, how do we go about? So we formulate this adaptation process as a variational inference problem, which incorporates the test sample as a conditional into the generation of model parameters. So here we have the test sample, the single test sample that we want to classify. This is the meta target set that we have during training, and that is the one we want to optimize. Now, this is nice, but it is intractable during inference because we don't have access to the target domain labels. So we approximate this by source domain similarity. So we approximate the model function theta t t with the accessible source data over here. And we use the variational inference approach. And by conditioning on this given sample xt and the source data s, the adapted variational distribution contains both the categorical information provided by the meta source data and the domain information given by the meta target sample. So while doing so, our model learns the ability to adapt the meta source model to each meta target instance across different domain shifts. And because it has encountered this all during training, the hope is that an unseen target at test time can also profit from this adaptation ability. Now, this is all nice in theory, but it also needs to be computational feasible. So rather than estimating all parameters of the model, we make a division between a shared feature extractor, phi, and a classifier w. And essentially, we only predict the parameters of the classifier w. And we keep the feature shared across domains. And here's another visualization of how this works. So this is what we have during meta training. We have a source domain or meta source domain from which we predict classifier parameters. Then we have from the meta target domain a single sample for which we know the label. And from this, we also predict classifiers, and it will be adapted based on the weight of the source domain to get the best possible label. Now, at test time, we don't have the label, but we still have the source domain data, and this will help to adapt the classifier for the single target sample. And because we rely on amortization inference network, we only need one forward pass. So there is no more fine-tuning needed. We just do one forward pass to get the classification result we want. We performed a comparison with test time adaptation, also known as TENT. And for this experiment, we rely on rotated MNIST, where we have 7 domains, each divided by 15. Each digit is divided by 15 degrees. And we use the images by 0, 45, and 90 as target domains, and the other 4 as the source domain. And then we first do a single target domain experiment. And let me explain what's going on in this plot. So here you see the accuracy. So this is rotated MNIST, so numbers are high. This is our approach, our single target sample approach, and all the other colors are tent. And because tent has fine tuning and it has a batch size, we plot here the number of samples in the batch. And we also show the number of iterations. So we can have tent with only one iteration, one optimization, or 100 up to 100 optimizations. Now, what we see is that tent works well with large batches of 128 samples, and especially if all the problems are from a single target domain. Now, if we make the setting a bit more complicated, so we no longer guarantee that the batch contains only samples from one target domain, but can also contain samples from multiple target domains, essentially tent starts to collapse, and it can no longer do, it no longer profits from the adaptation, so to say, where we have the same effect. We also compared with other methods and different base networks, and I think here, although there might be approaches that result in better results, I think the main takeaway here is that the better the base network, the more we gain, and we outperform similar test time adaptation approaches. So the one by Tent, by Wang et al., and also recent work from CVPR. Maybe this is insightful. So here we show some failure cases where we plot the classifiers, different classifiers that we have in the same feature space. And here is our target sample. And in this case, it predicts based on the closest other class, which is in this case is the person classifier. So that's a mistake. It should have been this one, the guitar classifier. Here's another example. So this is a horse, but it is predicted as being a house, probably because of the confusion in the background. And same here. So this is an elephant, but it's misclassified as a horse. The real class is close by, but not yet, not close enough. So this concludes my talk. So there is a need for real-world learning across domains, labels, tasks, and with fairness. To get there, we need to question common learning assumptions. And what I have shown is that label, task, and domain assumptions can be relaxed during learning and still generate good results. And with that, I would like to thank you for your attention.
Thanks, Cees. So, guys, if you have questions, so that's opportunity to ask Cees. You can write it in chat, or you can talk directly if you want. Let me start with a question just to warm up a bit. So I think it's quite inspiring, Cees, what you are doing, and of course, moving towards real world is important. But considering also your past life experience and so on, I was wondering, what about the modality gap in some sense? Can you comment on that?
Good question. So I didn't talk about multimodality, but I actually think that it is part of the solution. So if you have rich data like video, this correspondence between audio and visual is a very strong signal that would also limit the need for labels, and is also generalizes well again over domains. So that is a very powerful mechanism to make it happen, the real world learning.
Absolutely, and I think you can also consider some kind of cross-model type of things. I mean, you may have, in the first example, for example, you had support videos and so on. You may have some kind of support sound, and you can kind of connect that particular query sound to what you can find in video, for example, and vice versa.
Absolutely, absolutely, yeah.
Other questions, guys? Actually, I also have another. I have another question for the first application. I was wondering, with the support videos, are you assuming that the support videos are already segmented on the action, or you can just give them, they are longer videos without any information, and you can practically, in an unsupervised way, you are identifying what is the common action from there to be used as driving information.
Yeah, so what we assume is that they are short clips that contain the object or action of interest in a trimmed fashion, and that's it.
Okay. But if you relax this constraint, if you just practically give a video in which also there, that there is some action, and you can kind of, so that there is a video about, I don't know, a football game or a goal or whatever, but you don't have the segmentation there. Could you still...
Yeah, what do you mean with segmentation? The temporal segmentation?
The temporal segmentation, I mean, yes.
Yeah, so if we, it still works, but it becomes worse.
Of course.
So it starts to
deteriorate. You have a lot of noise, yes,
yeah,
of course.
Yeah. You add more noise essentially into the support.
And in that case, I mean, even if you have them, cropped in some sense, how do you deal with, let's say, the dynamic tar warping, in the sense that they may have at least in the temporal domain, maybe faster, longer, may have a lot of variations. So in the way the action is enacted.
Yeah, we have not really studied that dimension yet, so I don't dare to say much about it.
Okay,
it's a good point. Yeah.
Okay. Well, I guess you were so eloquent, Chris, that people. Well, I believe, as I said, I think it's quite interesting. I think all of us should kind of move towards real world information, and we should start releasing some of the assumptions that we are making. And I think the research of case in this, it's quite an important step in this direction. So I think we should all go into this type of analysis. Well, so if there are no further questions.
Yes, actually, I have a question.
Okay, go.
Well, what about the link of all these works with more traditional methods like one-class classification? Because we can consider that one-class classification might be a case where the support videos belong to the same class. So in one-class classification, you might not need label information. So can we see that as an evolution of one-class classification? Especially the first case, the learning without labels.
Yeah, it certainly has a relationship. It's been a while, the one-class classification, but yeah, you can say it is related. You can say so, yeah.
Yes. I mean, if we can say that this is the future, do you use the support videos to train the architecture, or the architecture is pre-trained and then
yeah, so we have a pre-trained network, in this case I3D, but we have a training process that tries to find the commonality and foreground and background, so to say. So, but at test we don't need any label, and also at training we never use a class label or whatsoever. So only this notion of commonality is used during training.
Okay.
Well, I have only one last comment case related to the failure cases that you show at the end. I think they are quite reasonable. Of course, you have ground truths and you expect that the model will understand what is in there. But I think even for a human being, it's quite difficult to tell. I mean, what you are looking for. You want the horse or you want the house behind, and all these type of things. I think the solution it's quite good.
Yeah, I think it's you can argue that for these domain shifts in images is still relatively straightforward.
Precisely.
Not too big a shift. So I think we also need harder benchmarks, so to say, and bigger changes between domains to really test how far we can get with these types of algorithms.
I agree. Okay, so thanks a lot, Cees. I think it was quite inspiring, and we really hope that many of us are going into this direction. So it's a huge field, and there are a lot of challenges to move, and you just started to kind of scratch a little bit the surface. So well, looking forward to seeing you all in person very soon, and Cees will talk very soon as well.
Yes, will do. Thanks a lot.
Thank you, guys.
Bye-bye.
Thank you.